Using the product, quotient, and chain rules together to find derivatives of functions. Recall the following: that we use the product rule for functions of the form y equals f times g, and the product rule states that the derivative then is the first function times the derivative of the second, plus the second function times the derivative of the first. We use the quotient rule for functions of the form y equals f divided by g, and the quotient rule states that the derivative is equal to the bottom function times the derivative of the top, minus the top times the derivative of the bottom, all divided by the bottom squared. And the chain rule is used for functions of the form y equals f composed with g, and the chain rule says that the derivative is the outside function times the derivative of the inside function. Well, there are some functions that may require the use of more than one rule. For example, the function y equals the quantity 1 minus x to the second power times the log of x contains both a product and a composite function. Therefore, we would have to use both the product rule and the chain rule to compute the derivative. So let's actually find the derivative of that function. Again, because there is both the product and a composite function, we'll have to apply the product rule and the chain rule. Start by applying the product rule formula, which says the first function, 1 minus x squared, times the derivative of the second, log of x, plus the second function, log of x, times the derivative of the first, 1 minus x squared. Now I'll compute those derivatives. The derivative of the log of x is 1 divided by x times the natural log of 10. The derivative of 1 minus x squared requires the chain rule. I must take the derivative of the outside function, the second power function, times the derivative of the inside function, 1 minus x. Well, that derivative becomes 2 times the quantity 1 minus x times negative 1. Simplifying, my final answer for the derivative is the quantity 1 minus x squared divided by x times the natural log of 10 minus 2 times the quantity 1 minus x times the log of x. Example 2, I want to find the derivative of y equals the square root of 5x plus 3 divided by the cotangent of x. Here I have both the quotient and a composite function. Therefore, I must use the quotient rule and the chain rule. Applying the quotient rule formula, the quotient rule says to take the function on the bottom, cotangent of x, and multiply by the derivative of the function on top, square root of 5x plus 3, minus the function on top, square root of 5x plus 3, times the derivative of the quotient on the bottom, cotangent of x, all divided by the bottom function squared. Computing those derivatives, well, the square root of 5x plus 3 is a composite function. My outside function is the square root function, or square root is the same as the 1/2 power, and my inside function is 5x plus 3. Therefore, I have to use the chain rule to compute that derivative. Well, the derivative then is the outside function. The derivative of the outside is 1/2 times 5x plus 3 to the negative 1/2 times the derivative of the inside. The derivative of 5x plus 3 is 5. In the second term, I compute the derivative of cotangent of x. The derivative of cotangent is negative cosecant squared. Putting it all together, I end up with 5/2 times the cotangent of x times 5x plus 3 to the negative 1/2 power plus the cosecant squared of x times 5x plus 3 to the positive 1/2 power, all divided by the cotangent of x squared. If I want to simplify this expression further, I start by multiplying every term in the numerator and in the denominator by 2. That cancels out that 5/2 and leaves me with 5 times the cotangent of x times the quantity 5x plus 3 to the negative 1/2 power plus 2 cosecant squared of x times the quantity 5x plus 3 to the positive 1/2 power, all divided by 2 cotangent squared of x. Next, I'll factor out the quantity 5x plus 3 to the negative 1/2 power from each term in the numerator. That leaves me with 5 cotangent of x plus 2 cosecant squared of x times the 5x plus 3 to the first power, and the denominator remains unchanged. Finally, I'll move that negative 1/2 power from the numerator into the denominator where it will become positive. So 5x plus 3 to the negative 1/2 power will move to the denominator where it becomes 5x plus 3 to the positive 1/2 power. But recall that the 1/2 power is the same as square root. So 5x plus 3 to the negative 1/2 in the numerator becomes 5x plus 3 to the positive 1/2 in the denominator, or that's the same as the square root of 5x plus 3. So my final answer for the derivative is 5 cotangent of x plus the quantity 5x plus 3 times the cosecant squared of x, all divided by 2 times the square root of 5x plus 3 times the cotangent squared of x. Our final example, we're asked to find the derivative of y equals 2 pi times the quantity sine cubed x minus cosine squared x. I'll start by rewriting those powers of sine and cosine so that I can more easily recognize them as composite functions. Sine cubed x is the same as sine of x to the third power, and cosine squared x is the same as cosine of x to the second power. Because these are composite functions, I now apply the chain rule. The chain rule says the outside function. In the first term, the outside function is the third power function, and the inside function is sine of x. So the derivative of the outside, 3, times the sine of x to the second power, times the derivative of the inside. The derivative of sine of x is cosine. Minus, in the second term, my outside function is the second power function, and my inside function is cosine. So the derivative of the outside is 2 times the cosine of x to the first power, times the derivative of the inside. The derivative of cosine is negative sine. So I end up with 2 pi times the quantity 3 sine squared x cosine of x plus 2 sine x cosine of x. There's a factor of sine x cosine of x in both terms, so I factor that out, and my final answer for the derivative is 2 pi sine of x cosine of x times the quantity 3 sine of x plus 2.